Imagine you could take one of the densest, most extreme objects in the universe, a neutron star, a dead stellar core so compressed that a single teaspoon of it weighs over 4 billion tons, and somehow shove it inside a living star. Not next to it, not orbiting it, inside it, buried deep in the belly of a red supergiant, still functioning, still burning, still looking almost normal from the outside. That sounds like it should be impossible. The neutron star should tear the giant apart. The giant should crush itself trying to contain it. Everything about this arrangement screams destruction. And yet, 2 physicists predicted that this exact object could exist. It even has a name, and astronomers may have already found one. Before we dive into this, if you find these kinds of deep explorations fascinating, a quick like or subscribe would genuinely help the channel keep going. It's a small thing on your end, but it makes a huge difference for me. Also, before we begin, we're now live on Spotify. The link's in the description if you'd like to listen to us wherever you are. Now, let's begin. Let's start with the neutron star. Because if you're going to understand why a Thorne Żytkow object sounds impossible, you first need to understand just how extreme the thing at its heart really is. A neutron star is not just another kind of star. It is something else entirely. It is what's left behind when a massive star dies in the most violent way the universe allows. And what remains after that death is one of the most extreme objects that physics permits to exist without crossing the threshold into a black hole. It is density beyond comprehension, gravity beyond anything you have ever encountered, and matter squeezed into a state so alien that nothing on Earth can even approximate it. Let me take you through what a neutron star actually is, because most people hear the name and think of something star-like. Something that glows, something that burns fuel, something that resembles the sun in some distant way. It does not. A neutron star does not burn anything. It does not sustain nuclear fusion in its core the way the sun does. It is not generating energy through the same processes that power ordinary stars. It is a dead core, a remnant, a corpse. But it is a corpse so dense and so gravitationally powerful that it warps space around it in ways that would be fatal to any ordinary matter that came too close. Here is how one forms. Take a star much more massive than the sun. Not twice as massive. Not 5 times. We are talking about stars that are at least 8 times the mass of the sun, and sometimes 20 or 30 times more massive. These are enormous stars. The kind that burn through their nuclear fuel far faster than smaller stars, because the crushing weight of their own gravity demands enormous energy output just to keep from collapsing. A star like the sun will live for about 10 billion years, steadily fusing hydrogen into helium in its core, comfortable and stable. A star 20 times the mass of the sun might last only about 10 million years. That sounds like a long time by human standards, but in stellar terms, it is a blink. These massive stars live fast and die violently. When such a star reaches the end of its life, it has burned through all the fuel it can use. It starts with hydrogen, fusing it into helium. Then, when the hydrogen was exhausted in the core, it fused helium into carbon and oxygen. Then carbon into neon, neon into oxygen, oxygen into silicon, and finally silicon into iron. This is where the process stops. Iron is the end of the line. Fusing iron does not release energy, it absorbs it. So when the core of a massive star fills with iron, there is no longer any outward pressure from fusion to support the star against its own gravity. The core collapses. And when I say collapses, I mean collapses. What happens next takes less than a second, and it is one of the most violent events in the known universe. The iron core, which might be roughly the mass of the Sun, but about the size of Earth, suddenly loses the pressure support that has been holding it up. Gravity wins instantly. The core plunges inward at speeds approaching a quarter of the speed of light. The inner part of the core compresses down to a sphere roughly 12 miles across in a fraction of a second. 12 miles. That is about the distance from one end of a medium-sized city to the other. All the mass that was spread across a volume the size of an entire planet gets crushed into something smaller than a single metropolitan area. The compression is so sudden and so extreme that the inner core actually overshoots its equilibrium. It squeezes tighter than even neutron degenerate matter wants to be. And then it rebounds. Like a rubber ball hitting a concrete floor, the inner core bounces back outward, launching a shockwave into the still falling outer layers of the core. This shockwave is the seed of the supernova explosion. But here is something that surprises most people. The shockwave alone is not powerful enough to blow the star apart. As it pushes outward through the infalling material, it loses energy. It stalls. It stalls within milliseconds, sitting partway through the core, not moving outward, while material continues to rain down on it from above. For a brief moment, the explosion fails. The star is caught between collapse and explosion, and collapse is winning. What revives the explosion is neutrinos. During the core collapse, an almost inconceivable flood of neutrinos is produced. Neutrinos are ghostly subatomic particles that barely interact with matter. Under normal conditions, they pass through solid objects as if those objects were not there. Trillions of neutrinos from the Sun pass through your body every second without touching a single atom. But in the collapsing core of a massive star, the densities are so extreme that even neutrinos get partially trapped. They deposit a fraction of their energy into the material behind the stalled shockwave, heating it, re-energizing it, and pushing it outward. This neutrino-driven mechanism is what finally blows the outer layers of the star into space. The energy carried by these neutrinos is staggering. Roughly 99% of the total energy released in a supernova is carried away by neutrinos, not by the visible light and kinetic energy of the explosion that we actually see. The brilliant flash that lights up a galaxy, the expanding shell of hot gas that astronomers observe for months, all of that represents only about 1% of the explosion's total energy output. The rest is invisible, carried away by particles that pass through the debris without stopping. What is left behind after this cataclysm is the neutron star. The compressed core, now a sphere roughly 12 miles across, containing more mass than the Sun. The density becomes almost impossible to describe. A single teaspoon of neutron star material would weigh roughly 4 billion tons on Earth. Let me say that again because it deserves to sit in your mind. A teaspoon. 4 billion tons. That is more than the combined weight of every building in a large city. Every car, every truck, every bridge, every piece of infrastructure that humans have ever built in that city, all compressed into a volume smaller than a sugar cube. The atoms themselves cannot survive this compression. Under the unimaginable pressure of gravitational collapse, electrons are forced into protons, and the two combine to form neutrons. This is why it is called a neutron star. The entire object is made almost entirely of neutrons, subatomic particles packed so tightly together that the star is essentially one enormous atomic nucleus. There are no atoms in a neutron star. There are no molecules, no compounds, no crystal structures in the usual sense, just neutrons, pressed against each other so tightly that the strong nuclear force, one of the fundamental forces of nature, is the only thing preventing further collapse into a black hole. But a neutron star is not a simple, uniform ball of neutrons from surface to center. It has internal structure, layers that are each stranger than the last as you go deeper. The outermost layer is a thin atmosphere, perhaps only a few centimeters thick, made of ordinary matter, mostly hydrogen and helium, heated to extraordinary temperatures by the star's residual heat and by any material falling onto it. Below the atmosphere is the crust. The crust of a neutron star is made of a crystalline lattice of atomic nuclei, arranged in a regular grid, surrounded by a sea of electrons. It is the hardest known material in the universe, billions of times stronger than steel. If you could somehow extract a piece of neutron star crust and bring it to Earth, it would be harder and more rigid than anything humans have ever encountered. The crust is thin, perhaps only about a mile thick, but it is strong enough to support small mountains on the neutron star's surface. Mountains that might be only fractions of an inch tall, but represent enormous structures given the extreme gravity pressing down on them. Beneath the crust lies the outer core, and here things become truly alien. The outer core is made of neutrons, protons, and electrons, but the neutrons exist in a state called a superfluid. A superfluid is a quantum state of matter in which a fluid flows without any friction or viscosity whatsoever. Under normal conditions, superfluids only exist in laboratories at temperatures close to absolute zero. Inside a neutron star, temperatures are hundreds of millions of degrees, yet the extreme pressures create conditions where superfluidity emerges anyway. This neutron superfluid can do bizarre things. It can flow without resistance, create quantized vortices, and rotate in ways that ordinary fluids cannot. The protons in the outer core are believed to form a superconductor, another exotic quantum state where electrical currents flow without resistance. This is part of what generates the neutron star's incredible magnetic field. And then there is the inner core. This is the deepest layer, the region at the very center of the neutron star, where the density reaches its most extreme values. And the honest truth is that we do not know exactly what exists there. The pressures and densities in the inner core exceed anything that can be reproduced in any laboratory on Earth. They exceed anything that our current theories of nuclear physics can fully describe. Some physicists believe that at these extreme conditions, neutrons themselves may break apart, dissolving into their constituent quarks, forming a state of matter called quark matter that has never been directly observed. Others propose even more exotic possibilities: strange matter containing a type of quark called a strange quark, or other phases of matter that exist only in the mathematics of quantum chromodynamics. The deep interior of a neutron star may contain forms of matter that exist nowhere else in the entire universe. We genuinely do not know. It is one of the great unsolved questions in physics, and it is sitting there, 12 miles across, inside every neutron star in the galaxy. The gravity on the surface of a neutron star is roughly 200 billion times stronger than gravity on Earth's surface. If you could somehow stand on a neutron star, which you absolutely could not because you would be torn apart and crushed into a thin film of matter long before you reach the surface. But if you could somehow stand there, you would weigh about 200 billion times your Earth weight. A person who weighs 150 pounds on Earth would weigh something on the order of 30 trillion pounds on a neutron star. The escape velocity, the speed you would need to travel to leave the surface, is roughly 100,000 kilometers per second. That is about 1/3 the speed of light, just to leave the surface. For comparison, the escape velocity from Earth is about 11 kilometers per second. Neutron stars also spin, and they spin fast. When the original star's core collapses, the same principle that makes an ice skater spin faster when they pull their arms in applies. The core was rotating slowly before the collapse. When it compresses down to 12 miles across, that rotation speeds up enormously. Some neutron stars spin hundreds of times per second. The fastest known neutron star rotates at over 700 times per second. That means the surface at the equator is moving at a significant fraction of the speed of light. These rapidly spinning neutron stars are called pulsars because they emit beams of electromagnetic radiation from their magnetic poles. As the star spins, these beams sweep across space like a lighthouse. If one of those beams happens to point at Earth, we detect a regular pulse of radiation, hence the name. The magnetic fields of neutron stars are equally extreme. A typical neutron star has a magnetic field about 1 trillion times stronger than Earth's magnetic field. Some neutron stars, called magnetars, have fields 1,000 times stronger still. These are the most powerful magnetic fields in the known universe. At close range, a magnetar's field would be strong enough to distort atoms, stretching them into long, thin cylinders aligned with the field. It would be lethal at a distance of 1,000 kilometers, not because of radiation, but because the magnetic field itself would disrupt the chemistry of your body at the molecular level. So that is a neutron star, a dead stellar core roughly 12 miles across, containing more mass than the Sun, born in one of the most violent events nature can produce, with a crystalline crust harder than anything in the universe, a superfluid interior, and possibly exotic quark matter at its center. Spinning hundreds of times per second, with gravity 200 billion times stronger than Earth's, and magnetic fields 1 trillion times more powerful. It is one of the most extreme objects in the entire universe. It is dense, violent, compact, and surrounded by conditions that would obliterate almost anything that came near it. Now let me take you to the other end of the spectrum. Let me show you what a red supergiant is, because the contrast between these two objects is so staggering that the idea of combining them feels like a contradiction in terms. A red supergiant is one of the largest types of star that exists. While a neutron star is 12 miles across, a red supergiant can be hundreds of millions of miles across. Some are over 1 billion miles in diameter. These are stars so enormous that if you placed one where the Sun is, its outer surface would extend past the orbit of Mars. In some cases, past the orbit of Jupiter. The star Betelgeuse, the bright reddish star marking the shoulder of the constellation Orion, is a red supergiant with a diameter roughly 700 times that of the Sun. If Betelgeuse replaced our Sun, Earth would be deep inside the star, orbiting within its outer layers. Mars would be inside it too. The outer surface would reach well past Mars, extending out toward the asteroid belt. But here is the thing that most people do not realize about red supergiants. Despite being enormous in size, they are not dense. In fact, they are extraordinarily diffuse. The outer layers of a red supergiant are so thin, so sparse, that they are barely more substantial than a laboratory vacuum. The gas in the outer envelope of a red supergiant can have a density millions of times lower than the air you're breathing right now. If you could somehow fly a spacecraft into the outer layers of a red supergiant, you might not even notice you had entered the star at first. The gas would be so thin that it would be almost indistinguishable from the near vacuum of space. It would get denser as you went deeper, certainly, but the outermost layers are almost nothing. They are enormous volumes of extremely sparse gas, glowing faintly red because the surface temperature is relatively cool by stellar standards, typically around 3,000 to 4,000 degrees Celsius. That sounds hot, and it is hot compared to anything on Earth. But compared to the Sun, whose surface temperature is about 5,500 degrees Celsius, and especially compared to the hottest stars, which can reach 50,000 degrees or more, a red supergiant is cool. Its surface is cool, its outer envelope is thin, and its enormous size comes not from being packed with material, but from being puffed up, inflated by radiation pressure and convection from the interior. Think about the difference for a moment. A neutron star is 12 miles across and contains more mass than the Sun. A red supergiant might be 1 billion miles across, but its outer layers are thinner than the air in the room you're sitting in right now. One is matter compressed to the absolute limit, squeezed to densities that defy comprehension. The other is matter spread so thin that it is barely there. One has surface gravity 200 billion times stronger than Earth's. The other has surface gravity so weak that its outer layers are actively drifting away into space in the form of stellar winds. Red supergiants lose enormous amounts of mass through these winds, sometimes shedding the equivalent of an entire Earth's mass every few years. Their hold on their own material is precarious. They are, in a sense, stars that are already falling apart. And this brings us to the heart of the matter. Because when you put these two objects side by side, when you consider what each one is in physical terms, the idea of combining them, of putting one inside the other, of taking a neutron star and placing it at the center of a red supergiant, the reaction of any reasonable person should be that this cannot possibly work. Think about it. You have a neutron star with gravity so intense that it warps space, with a surface where matter falling inward hits at roughly 1/3 the speed of light, with magnetic fields that can tear atoms apart. And you are proposing to put that inside a star whose outer layers are barely denser than empty space. The neutron star would not gently sit there. It would devour material. Gas from the supergiant's interior would fall onto the neutron star, accelerating to extraordinary speeds, releasing enormous amounts of energy on impact. The energy released by matter falling onto a neutron star is not trivial. It is one of the most efficient energy release mechanisms in the universe, converting roughly 10 to 20% of the infalling matter's rest mass energy into radiation. For comparison, the nuclear fusion that powers ordinary stars converts less than 1% of the matter's rest mass energy into radiation. A neutron star accreting material is, pound for pound, over 10 times more efficient at generating energy than the process that lights every star in the sky. So you would expect the neutron star to generate so much energy from accreting the supergiant's interior material that it would blow the star apart. Or you would expect the neutron star to spiral deeper and deeper into the star, consuming everything in its path, growing more massive until it collapses into a black hole. Or you would expect the whole arrangement to become unstable in some spectacular way, producing an explosion or a collapse or some other form of destruction. you would not expect it to just sit there, quietly, looking like a normal red supergiant from the outside, producing light and heat as if nothing unusual were happening inside. And yet, that is exactly what Kip Thorne and Anna Żytkow proposed in 1975. Thorne was an American theoretical physicist who would later win the Nobel Prize in Physics in 2017 for his contributions to the detection of gravitational waves. Żytkow was a Polish-born astrophysicist who had done extensive work on stellar evolution and binary star systems. Together, they published a paper that asked a seemingly absurd question. What would happen if a neutron star ended up inside a red supergiant? Not orbiting around it, not in a binary pair with it, inside it, embedded in its interior, sitting where the normal stellar core should be. Their answer was surprising. They argued that under the right conditions, such an object could exist. Not forever, perhaps, but for a significant period, potentially hundreds of thousands of years, maybe longer. During that time, the object would look from the outside almost indistinguishable from a normal red supergiant. It would have a similar size, a similar surface temperature, a similar luminosity. An astronomer observing it through a telescope would see what appeared to be an ordinary giant star, maybe a bit unusual in certain details, but nothing that would immediately scream that there is a neutron star buried inside this thing. They called this theoretical object a Thorne Żytkow object, and the proposal immediately raised a wave of fascination and skepticism in the astrophysics community. Fascination because the idea was extraordinary. A star with a neutron star for a heart, a living stellar body wrapped around one of the densest, most extreme objects in the universe. Skepticism because the physics seemed like it should forbid it. How could such a configuration survive? How could the enormous energy released by accretion onto the neutron star not destroy the envelope? How could the whole thing not collapse or explode? The key to understanding why this idea is not immediately absurd, even though it certainly sounds like it should be, lies in understanding the difference between what a neutron star does in isolation and what it might do when surrounded by a vast envelope of low-density gas. In isolation, a neutron star accreting material from a companion star in a binary system produces X-rays, flares, jets, and enormous amounts of radiation. The material falls from a relatively thin accretion disk onto the neutron star's surface, hitting it at tremendous speeds and releasing energy that we can detect across thousands of light years. But inside a supergiant, the situation is fundamentally different. The neutron star is not pulling material from a distant companion through the vacuum of space. It is immersed in material. It is surrounded on all sides by the star's interior. The accretion is not a thin stream hitting a hard surface. It is a slow, enveloping flow of material falling from all directions. And the energy released does not escape into space. It is released inside the star. That energy gets absorbed by the surrounding envelope, heating it, driving convection, changing the internal structure of the star, but not necessarily destroying it. The envelope is enormous. It has a tremendous capacity to absorb energy. The energy released by accretion onto the neutron star can be carried outward by convection and radiated away from the star's surface without blowing the whole thing apart. At least in principle, at least under the right conditions. This is the essential insight of Thorne and Żytkow's work. The supergiant's envelope acts as a buffer, a shock absorber, a vast reservoir that can absorb the neutron star's ferocious energy output and redistribute it. The neutron star sits at the center, accreting material, releasing energy, but the envelope handles that energy through the same mechanisms it would use to handle the energy from a normal stellar core, through convection, radiation, and gradual transport outward. The result is a star that looks roughly normal from the outside, but has something profoundly abnormal at its center. Of course, this explanation raises as many questions as it answers. How does the neutron star end up inside the supergiant in the first place? You cannot just take a neutron star and drop it into a red supergiant like dropping a marble into a bowl of water. There has to be a mechanism, a sequence of events, a physical process that brings these two objects together and results in one being inside the other. And that process, as we will see, requires a very specific and somewhat unlikely chain of events involving binary star systems, stellar evolution, and a phenomenon called common envelope evolution. But before we get there, let me make sure the central paradox is clear, because this is what makes Thorne Żytkow objects so fascinating and so difficult to accept. A neutron star is one of the most extreme objects in the universe. It has gravity that warps space and time, density that exceeds anything else except a black hole, magnetic fields that can destroy matter at a distance, internal layers that may contain forms of matter found nowhere else in nature. And the proposal is that you can take this object and hide it inside a gentle, diffuse, slowly evolving red supergiant. And the result looks almost normal from the outside. It is like hiding a nuclear reactor inside a cloud. It is like embedding a jet engine inside a soap bubble and having the soap bubble survive. Everything about your intuition says this should fail spectacularly. Everything about the physics of neutron stars says the accretion energy should tear the envelope apart. Everything about the physics of stellar interiors says that a foreign compact object sitting at the center should disrupt the star's equilibrium. And yet the math, at least under certain conditions, says it might work. That is what makes this one of the most unusual ideas in all of astrophysics. It is not just strange. It is the kind of strange that challenges your basic assumptions about how stars work. When you learn about stellar structure in a physics course, you learn that stars are self-regulating systems. A star adjusts its temperature, pressure, and energy output to maintain a balance between gravity pulling inward and pressure pushing outward. This balance, called hydrostatic equilibrium, is what makes stars stable. It is what allows the sun to shine steadily for billions of years without collapsing or exploding. A Thorne Żytkow object challenges this picture because the energy source at the center is not nuclear fusion in the traditional sense. It is accretion onto a neutron star, which is a fundamentally different process with different characteristics and different feedback mechanisms. Whether such a system can maintain something like hydrostatic equilibrium, whether it can be stable in any meaningful sense, is precisely the question that has kept astrophysicists arguing for 5 decades. And the remarkable thing is that the argument is still going on. Since Thorne and Żytkow's original paper in 1975, dozens of subsequent studies have explored the idea. Some have supported it, finding that stable or quasi-stable configurations might be possible under specific conditions. Others have challenged it, finding that the energy released by accretion should be too much for the envelope to absorb, or that the configuration should rapidly evolve into something else, a collapse, an explosion, or a rapid spiraling of the neutron star that ejects the envelope entirely. The theoretical picture is not settled. It is still an active area of research. What is settled is that the idea is physically plausible enough to be taken seriously by the astrophysics community. It is not science fiction. It is not pure speculation. It is a legitimate theoretical prediction, published in peer-reviewed journals, studied by serious researchers with specific observational signatures that astronomers can look for. Whether nature actually produces these objects is another question entirely, and one we will explore in depth. But the fact that the idea has survived 50 years of scrutiny without being conclusively ruled out tells you something important about how the universe works. The universe is stranger than our intuition suggests. The things we think should be impossible sometimes turn out to be merely improbable, and the boundaries between what can exist and what cannot are often far more subtle than they appear. So that is where we stand. We have a neutron star, 12 miles across, dense beyond comprehension, with gravity that warps space-time, born in a cataclysm that releases more energy in neutrinos alone than the sun will produce in its entire lifetime, harboring layers of matter so exotic that physicists are still arguing about what they are made of. And we have a red supergiant, hundreds of millions of miles across, diffuse and tenuous, with outer layers thinner than the air around you. Two objects at opposite extremes of stellar physics. And the question at the heart of everything that follows is this: how could one end up inside the other? And if it did, what would happen next? To understand how a neutron star could end up inside another star, you need to understand something fundamental about how stars live and die in the universe. Most people picture stars as solitary objects, lonely points of light separated by vast gulfs of empty space. And some stars are like that. The sun is essentially a loner. It does not have a stellar companion. It orbits the center of the Milky Way on its own, accompanied only by its planets and debris. But the sun is not typical in this regard. The majority of massive stars, the kind of stars that eventually produce neutron stars when they die, do not exist alone. They exist in pairs, sometimes in triples, sometimes in even larger groups. But most commonly, they exist in binary systems. Two stars orbiting each other, bound together by gravity, dancing around a common center of mass for millions of years. This is not a rare arrangement. Among stars more than about 8 times the mass of the sun, binary systems are the norm, not the exception. Estimates suggest that somewhere between 60 and 70% of all massive stars have at least one stellar companion. Some surveys put the number even higher. The universe, when it comes to massive stars, is a place of partnerships. Stars form together out of the same collapsing cloud of gas and dust, and they often end up gravitationally bound to each other from birth. These binary systems are the starting point for nearly everything that follows in the story of Thorne Żytkow objects. Without binary stars, this entire concept would be impossible. You need 2 stars. You need them close enough to interact, and you need them to have the right combination of masses and orbital properties for the sequence of events to unfold. So let us set up the scenario. Imagine a binary system containing 2 massive stars. One is perhaps 25 times the mass of the sun. The other is perhaps 15 times the mass of the sun. They orbit each other at a distance of maybe a few 100 million miles, close enough that their gravitational influence on each other is significant but far enough apart that they are not touching or exchanging material. At least not yet. For millions of years, both stars burn hydrogen in their cores, shining brilliantly, living their lives in tandem. They are hot, luminous, blue or blue-white stars, each one thousands or tens of thousands of times more luminous than the Sun, they are spectacular objects, among the most impressive things the universe produces. But massive stars do not live long. The more massive a star is, the faster it burns through its fuel. And in this binary system, the two stars have different masses, which means they will not die at the same time. The more massive star, the one that is 25 times the mass of the Sun, will exhaust its fuel first. It will go through all the stages of nuclear burning, hydrogen to helium, helium to carbon, carbon to neon, all the way to iron, and then its core will collapse. Depending on the exact mass and other details, this collapse will produce a supernova explosion, one of the most energetic events in the universe. The outer layers of the star will be blasted into space at speeds of thousands of kilometers per second, creating an expanding shell of hot gas that will glow for weeks or months. And at the center, where the core was, a neutron star will be left behind. Or, if the star was massive enough, a black hole. But for our story, let us assume the remnant is a neutron star. Roughly 12 miles across, roughly 1.5 times the mass of the Sun. Dense beyond comprehension. Now here is where things get interesting, and also where things get precarious. The supernova explosion does not happen gently. It is an asymmetric, violent event. The explosion can give the newborn neutron star a kick, a burst of velocity in a particular direction, caused by asymmetries in the explosion itself. These natal kicks can be substantial, sometimes hundreds of kilometers per second. This is a serious problem for the binary system. If the kick is too large, or if more than half the total mass of the system is lost in the explosion, the binary can be disrupted. The neutron star goes flying off in one direction, the surviving companion goes flying off in another, and the system is destroyed. No binary means no interaction, which means no Thorne Żytkow object, and the odds are not great. When a massive star explodes as a supernova, it ejects most of its mass. A star that was 25 times the mass of the Sun might leave behind a neutron star of only 1.5 solar masses. The rest, more than 20 solar masses of material, gets blasted into space. That is an enormous amount of mass suddenly leaving the system. The gravitational glue holding the binary together weakens dramatically in an instant. If the mass loss is too sudden and too large, the remaining gravitational attraction between the neutron star and the surviving companion is not enough to keep them bound. The system flies apart. Studies of binary systems in the Milky Way suggest that the majority of binaries containing massive stars are disrupted by the first supernova. The surviving companion becomes a runaway star, a massive star hurtling through space at high velocity, no longer bound to anything. And the neutron star goes its own way, joining the population of isolated neutron stars, drifting through the galaxy. Most massive binary systems do not survive the death of their first member. That is a sobering fact for the Thorne Żytkow story, because it means the starting conditions are already rare. But sometimes, the binary survives. If the kick is small enough, or if it happens to be directed in a way that does not unbind the system, or if the mass loss is not too extreme, the two objects remain gravitationally bound. You now have a binary system consisting of a neutron star and a massive star. The neutron star is small, dark, and incredibly dense. The companion star is still alive, still burning fuel, still shining. The orbit may have changed. It may be wider or more eccentric than before, altered by the mass loss and the kick. In many cases, the orbit becomes highly elliptical, with the two objects swinging close together at one point and far apart at another. tracing elongated paths around their common center of mass. But the system is intact, and the clock is ticking. What happens next is a waiting game. The companion star, the surviving one, is also massive, and massive stars do not last forever. But it is less massive than the star that already died, which means it evolves more slowly. Depending on its exact mass, it might have millions of years of main sequence life remaining. During this time, the binary is relatively quiet. The neutron star orbits alongside the companion, invisible to most telescopes unless it happens to be accreting a small amount of material from the companion's stellar wind, in which case it might show up as a faint X-ray source. But nothing dramatic is happening yet. The system is waiting for the companion to age. Eventually the companion exhausts its core hydrogen, then its core helium, and begins to evolve off the main sequence. As it does, it will expand. Its outer layers will swell outward, driven by changes in the star's internal structure as it transitions from one stage of nuclear burning to the next. It will grow from a compact blue star into a bloated giant, then into an even more bloated supergiant. Its diameter might increase from perhaps 10 or 20 times the size of the Sun to hundreds of times the size of the Sun. In some cases, the expansion can carry the star's surface to thousands of times its original radius. This expansion is not instantaneous. It happens over hundreds of thousands of years. Gradually, as the star's interior restructures itself, the core contracts and heats up. The envelope responds by expanding and cooling. The star moves across what astronomers call the Hertzsprung-Russell diagram, shifting from the hot blue side to the cool red side as its surface temperature drops and its radius increases. The companion, which was once a brilliant blue star, becomes a red supergiant, vast and diffuse, its outer layers extending hundreds of millions of miles into space. And this is where the binary nature of the system becomes critical. Because the companion star is not expanding into empty space, it is expanding toward another object, the neutron star, which is orbiting nearby. As the companion swells, its outer layers can reach the orbital distance of the neutron star. When this happens, the neutron star is no longer orbiting in empty space outside the companion. It is now orbiting inside the companion's outer layers. It has been engulfed, swallowed, enveloped by the expanding star. This process has a name. Astrophysicists call it common envelope evolution. And it is one of the most dramatic and consequential processes in all of binary star physics. Common envelope evolution is exactly what it sounds like. Two objects, in this case a neutron star, and the core of the expanding companion star, end up sharing a single common envelope of gas. The envelope belongs to the companion star. It is the companion's outer layers, the vast, diffuse, puffed up material that expanded outward as the star evolved. But now both objects are inside it. The neutron star, which was orbiting outside the companion, is now plowing through the companion's envelope, surrounded on all sides by stellar material. And here is the crucial part. The neutron star does not just coast through this material without consequence. As it moves through the envelope, it experiences drag. Just as a ball experiences resistance when you push it through water, the neutron star experiences resistance as it moves through the gas of the companion's envelope. This drag force is not trivial. Even though the gas in the outer envelope is incredibly diffuse, the neutron star is moving at orbital velocities, tens or hundreds of kilometers per second, and it is extraordinarily dense and compact. The interaction between the fast-moving compact object and the surrounding gas creates a gravitational wake, a region of enhanced density behind the neutron star where gas piles up. This wake exerts a backward pull on the neutron star, slowing it down. It is like running through increasingly thick fog, except the fog is stellar plasma and the runner is a neutron star. Think about what this looks like from the neutron star's perspective. If we can anthropomorphize for a moment, you are a 12-mile wide ball of compressed matter, more massive than the sun, and you're plowing through gas at tens or hundreds of kilometers per second. The gas in the outermost layers is so thin, it barely registers. It is like moving through a near vacuum. But as you spiral inward, the gas gets denser. What started as something thinner than air becomes something more substantial. Not dense by terrestrial standards, not even close, but dense enough that at your velocity and with your gravitational reach, you are scooping up enormous quantities of it. You are dragging a wake of compressed gas behind you. You are heating the gas around you through friction and gravitational interaction. You are dumping energy into the envelope at a prodigious rate. And with every orbit, you lose a little more speed. Your orbit shrinks, you spiral deeper. The gas gets denser still. The drag increases. The process accelerates. As the neutron star slows down, it loses orbital energy. And when an orbiting object loses energy, it spirals inward. This is the same principle that governs satellites in low Earth orbit. If a satellite experiences atmospheric drag, it slows down and its orbit decays, bringing it closer to Earth. The same thing happens to the neutron star inside the common envelope. It loses energy to the surrounding gas and spirals inward, moving closer and closer to the companion star's core. This inspiral process is not instantaneous. It takes time. The exact timescale depends on the density of the envelope, the mass of the neutron star, the orbital velocity, and a host of other factors. But theoretical estimates suggest it could take anywhere from a few hundred years to a few thousand years. In astronomical terms, that is the blink of an eye. In human terms, it is still a long time, but the point is that the inspiral happens relatively quickly once the common envelope phase begins. Now, what happens during this inspiral is critically important, because the neutron star is not just passively sinking, it is actively interacting with the surrounding material. As it spirals inward, it is accreting some of the gas it passes through. Material falls onto the neutron star, releasing energy. And the drag itself converts orbital energy into thermal energy in the envelope, heating the surrounding gas. This energy injection into the envelope has consequences. It can unbind some of the envelope material, ejecting it from the system entirely. In many cases, the energy deposited by the inspiraling compact object is enough to eject most or even all of the envelope, leaving behind just the compact object and the exposed core of the companion star. When this happens, the result is a tight binary system consisting of a neutron star and a stripped stellar core, typically a helium star or a white dwarf, orbiting very close together. This is how many of the tight neutron star binaries we observe in the universe are thought to have formed. Common envelope evolution is a well-established theoretical framework, not just something invented for Thorne Żytkow objects. It is used to explain the formation of X-ray binaries, double neutron star systems, and many other observed phenomena in stellar astrophysics. But here is where the Thorne Żytkow path diverges from the more common outcomes. In the standard picture, the energy deposited by the inspiral ejects the envelope, and you end up with a tight binary. Or if the energy is insufficient to eject the envelope, the two objects merge catastrophically, producing an explosion or a collapse. These are the two most commonly discussed outcomes: envelope ejection or destruction. But Thorne and Żytkow proposed a third possibility. They proposed that under certain conditions, the neutron star could spiral all the way down to the center of the companion star and settle there without ejecting the envelope and without causing an immediate catastrophic event. The neutron star would replace the companion's original core, taking up residence at the center of the star, surrounded by the massive hydrogen and helium-rich envelope. The result would be a star that looks like a red supergiant from the outside, but has a neutron star at its center instead of a normal stellar core. This third possibility requires very specific conditions. If the companion star's envelope is too loosely bound, the energy from the inspiral will eject it, and you get a stripped binary, not a Thorne Żytkow object. If the companion's core is too massive or too compact, the merger might trigger an immediate collapse or explosion, rather than settling into a quasi-stable configuration. The mass ratio between the neutron star and the companion matters enormously. The orbital parameters at the start of the common envelope phase matter. The evolutionary state of the companion matters. How much of the envelope gets ejected during the inspiral matters. The details of how energy is transported and radiated within the envelope matter. Getting all of these factors into the right range to produce a Thorne Żytkow object rather than one of the more common outcomes is thought to be relatively unlikely. This is one of the reasons why Thorne Żytkow objects, if they exist, are expected to be rare. The formation channel is narrow. Many things have to go right, or more precisely, many things have to go in a very specific way for the neutron star to end up at the center of the companion rather than ejecting the envelope or causing a catastrophe. But there is another possible formation path that does not involve common envelope evolution at all. In some binary systems, the supernova that creates the neutron star can give it a natal kick that sends it directly toward the companion star. If the kick is in exactly the right direction and the geometry is favorable, the neutron star could physically collide with the companion and plunge into it. This is sometimes called a direct collision or direct impact scenario. It is even less likely than the common envelope route because it requires the kick to be aimed almost perfectly at the companion. Even a small angular deviation would send the neutron star sailing past. Let me explain why the precision required is so extreme. The companion star, even if it is a large, massive star, occupies a tiny fraction of the sky as seen from the location of the supernova. Imagine standing at the point where the neutron star is born and looking in every possible direction. The companion star, even at a distance of only a few 100 million miles, subtends a tiny angle. For the natal kick to send the neutron star directly into the companion, the direction of the kick has to be aimed within that tiny angle. The chances of this happening randomly are very small. It is like throwing a dart blindfolded in a random direction and hitting a specific apple on a table across the room. Possible in principle, extraordinarily unlikely in practice, and even if the kick does aim the neutron star at the companion, the collision is not a simple event. The neutron star approaches the companion at tremendous speed, potentially hundreds of kilometers per second. When it hits the outer layers of the companion, it begins to decelerate. But its momentum is enormous because despite being only 12 miles across, it has a mass greater than the sun. The neutron star plunges through the outer layers, decelerating as it goes, depositing energy into the gas it passes through. Whether it can slow down enough to be captured, to stop inside the companion rather than punching straight through and coming out the other side, depends on the density profile of the companion, the speed of the neutron star, and the angle of impact. A head-on collision at moderate speed into a dense companion might work. A glancing blow at high speed probably would not. The neutron star might plow through the outer layers, heat them violently, but emerge on the other side, having passed through the companion without being captured. Or it might deposit so much energy on the way in that it disrupts the outer layers of the companion entirely, creating a spectacular explosion, but not a Thorne Żytkow object. But in a universe with hundreds of billions of massive binary systems in each galaxy, and trillions of galaxies in the observable universe, even extremely unlikely events can happen. Somewhere, sometime, a neutron star might have been kicked directly into a companion star and punched through its outer layers, decelerating as it went, sinking toward the center, and eventually settling into a Thorne Żytkow configuration. Let me address the obvious question that has probably been building in your mind. Why does the neutron star not simply destroy the supergiant from the inside? Why does this arrangement not immediately blow itself apart? This is the question that makes the Thorne Żytkow idea so counterintuitive. And the answer is subtle. It comes down to the difference between the rate of energy input and the rate at which the envelope can process that energy. When the neutron star first enters the envelope and begins spiraling inward, the energy release is indeed enormous. But the envelope of a red supergiant is also enormous. It contains a vast amount of gas spread over a volume that might be 1 billion miles across. This gas has a tremendous capacity to absorb energy. Energy deposited in one region of the envelope gets redistributed by convection, carried outward in rising plumes of hot gas, radiated from the surface, and generally spread out over the entire structure. The envelope acts like a giant thermal buffer. As long as the rate of energy input from the neutron star does not exceed the rate at which the envelope can absorb, redistribute, and radiate that energy, the envelope can survive. The star adjusts. Its structure changes. It might become more luminous or larger or change its internal temperature profile, but it does not explode. It finds a new equilibrium, or at least a quasi-equilibrium, a state that is not perfectly stable, but is stable enough to persist for a significant period. This is not so different from what happens in ordinary stars. The sun's core produces an enormous amount of energy through nuclear fusion. That energy doesn't immediately blast the sun apart because the sun's envelope absorbs it, transports it outward through radiation and convection, and radiates it from the surface in an orderly fashion. The star is in equilibrium. A Thorne Żytkow object is in a similar state, except the energy source at the center is accretion onto a neutron star rather than nuclear fusion. The physics is different, but the principle of energy balance is the same. The key requirement is that the neutron star's energy output must be manageable. If the neutron star accretes material too quickly, if it releases too much energy too fast, the envelope cannot cope and the star will be disrupted. This places limits on the accretion rate and therefore on the amount of material falling onto the neutron star. Theoretical models suggest that in a Thorne Żytkow object, the accretion rate onto the neutron star is actually quite low compared to what we see in X-ray binary systems, where a neutron star is actively pulling material from a nearby companion. Inside the supergiant, the material falls onto the neutron star slowly, fed by a gradual inward flow rather than a violent stream. The energy output is correspondingly moderate. Intense by any normal standard? Yes, but moderate enough that the vast envelope can handle it. There is another factor that helps. In an ordinary red supergiant, the core is a small, dense region surrounded by the vast envelope, and energy flows outward from core to surface. In a Thorne Żytkow object, the neutron star at the center is extraordinarily small compared to the envelope. It is 12 miles across, sitting at the center of a star that is hundreds of millions of miles across. The mismatch in scale is staggering. The neutron star is like a grain of sand in the middle of a stadium. The energy it releases is concentrated in a tiny region at the very center, and it must propagate outward through an enormous volume of gas to reach the surface. Along the way, it gets absorbed, reprocessed, and redistributed many times over. By the time the effects of the neutron star's energy output reach the surface of the star, they have been smoothed out, diluted, and blended with the rest of the star's thermal energy. The surface barely notices. This is why a Thorne Żytkow object could theoretically look almost indistinguishable from an ordinary red supergiant when viewed from the outside. The telltale signs of the neutron star at the center are hidden beneath hundreds of millions of miles of stellar envelope. The light reaching your telescope is surface light, and the surface of a Thorne Żytkow object is cool, red, and diffuse, just like any other red supergiant. The secret is buried deep inside where no telescope can directly see it. But almost indistinguishable is not the same as perfectly indistinguishable. And that difference, that subtle gap between looking exactly like a normal supergiant and looking almost like one, is where the story takes its next turn. Because the neutron star at the center of a Thorne Żytkow object does not just sit there passively absorbing material, it processes that material. It transforms it. Material that falls onto the surface of a neutron star undergoes nuclear reactions that are completely different from anything that happens in the core of a normal star. And those reactions produce elements, specific isotopes, distinctive chemical fingerprints that should not exist in ordinary red supergiants. These chemical fingerprints, if they could be detected in the surface layers of an apparently normal red supergiant, would be the smoking gun. The evidence that what you are looking at is not an ordinary star at all. It is something far stranger. Something with a neutron star for a heart. And that raises the next question. What exactly happens to matter when it falls onto a neutron star buried inside a supergiant? What kind of nuclear reactions occur? What elements are produced? And how would those elements ever make it from the neutron star at the center all the way up to the surface where we could detect them? Because the answers to those questions are what separate the Thorne Żytkow object from pure theoretical speculation and turn it into something astronomers can actually look for. The theory does not just predict that these objects exist. It predicts what they should look like, what they should contain, and how they should differ from the stars they mimic. It gives us a recipe for detection. And that recipe centers on some of the most unusual chemistry the universe has ever produced. Now, we need to go inside. We need to understand what is actually happening in the interior of a Thorne Żytkow object. Because this is where the physics becomes truly unlike anything else in the universe. This is where the object stops being merely an unusual stellar configuration and becomes something fundamentally new. A type of star that operates on principles completely different from every other star we know. And the key to everything, The key to understanding why these objects might betray themselves, even while wearing the disguise of a normal red supergiant, lies in what happens to matter when it meets a neutron star that is buried inside hundreds of millions of miles of stellar gas. Let us start by picturing the interior structure. In a normal red supergiant, the star has a layered architecture. At the very center is a dense core, where nuclear fusion is taking place. This core might be made of helium or carbon and oxygen, or heavier elements depending on how far the star has progressed through its evolutionary stages. Surrounding that core is a vast envelope of mostly hydrogen and helium gas. Energy produced in the core flows outward through this envelope, carried by radiation and by convection, the rising and sinking of hot and cool gas in enormous circulating plumes. Eventually, the energy reaches the surface and is radiated into space as the light we see through our telescopes. The core is small and hot. The envelope is enormous and relatively cool. The whole structure is held together by a balance between gravity pulling inward and pressure pushing outward. In a Thorne Żytkow object, the overall architecture looks similar from a distance. You still have a vast envelope of hydrogen and helium-rich gas. You still have a surface that is cool and red, radiating energy into space. But the center is completely different. Where the normal core should be, where there should be a ball of dense gas undergoing nuclear fusion, there is instead a neutron star, 12 miles across, 1.5 times the mass of the Sun, unimaginably dense, sitting at the exact center of the star like a tiny, impossibly heavy seed embedded in the heart of an enormous fruit. The region immediately surrounding the neutron star is extraordinary. Gas from the envelope, pulled inward by the neutron star's gravity, falls toward its surface. This infalling material does not arrive gently. Even though the flow rate is slow, compared to what you see in an X-ray binary system, the material is still being pulled by the gravitational field of an object with a surface gravity 200 billion times that of Earth. By the time the gas reaches the vicinity of the neutron star's surface, it has been accelerated to enormous speeds and compressed to extreme densities. The material piles up on the neutron star's surface in a thin, incredibly hot layer, and in that layer, nuclear reactions begin. But these are not the nuclear reactions you find in an ordinary star. In a normal stellar core, nuclear fusion builds lighter elements into heavier ones through well-understood processes. The Sun, for example, fuses hydrogen into helium through what is called the PP chain, a series of reactions that combine 4 hydrogen nuclei into one helium nucleus, releasing energy along the way. More massive stars use a faster process called the CNO cycle, which achieves the same end result, hydrogen into helium, but uses carbon, nitrogen, and oxygen as catalysts. At later stages of a massive star's life, fusion proceeds to heavier elements. Helium fuses into carbon, carbon into neon, neon into oxygen, and so on, all the way to iron. These processes are driven by the extreme temperatures and pressures at the center of the star, and they produce a predictable set of elements in predictable ratios. Stellar nucleosynthesis in ordinary stars is well understood. We know what elements a normal star should produce, and in roughly what quantities. The nuclear burning that occurs on the surface of a neutron star embedded in a supergiant is fundamentally different. The temperatures and densities at the neutron star's surface are far higher than what you find in any normal stellar core. Temperatures can reach billions of degrees. The density of the infalling material as it accumulates on the neutron star is extraordinary. Under these conditions, nuclear reactions proceed along pathways that simply do not occur in ordinary stars. Protons from the infalling hydrogen-rich gas are captured by existing nuclei at extremely rapid rates, building up heavier and heavier elements through a chain of proton captures and beta decays. This process is called the rapid proton capture process, or the RP process. But in a Thorne Żytkow object, there is an important twist. The RRP process does not proceed in the same clean, uninterrupted fashion that would in other astrophysical environments, such as the surface of a neutron star in an X-ray burst. In a Thorne Żytkow object, the material on the neutron star's surface is not isolated. It is constantly being mixed with fresh material falling in from the surrounding envelope, and material that has undergone nuclear processing on the neutron star's surface can be carried back outward into the envelope by convective motions. The nuclear burning gets interrupted. Products of the RP process are swept away before the reaction chain can run to completion, carried upward into cooler regions where the reactions stop. This interrupted version of the process is sometimes called the Interrupted Rapid Proton Capture Process, or the IRP process, and it produces a very specific and unusual set of elements. Let me explain why this matters so much. In ordinary stars, the elements produced by nuclear burning stay in the core or in the burning shells where they were created. They do not make it to the surface, at least not in the quantities or forms that would be easy to detect. The surface composition of a normal star mostly reflects the composition of the gas cloud from which it formed, with some modifications due to mixing processes that can dredge up small amounts of core material. But the overall chemical fingerprint of a normal star's surface is relatively predictable and well understood. In a Thorne Żytkow object, the situation is radically different. The interior of the star is dominated by a single enormous convective zone that extends from the regions near the neutron star all the way out to the surface. Material is constantly circulating. Hot gas rises from near the center, carrying with it the products of nuclear burning on the neutron star's surface. This material mixes into the envelope, gets carried to the surface, and leaves its chemical fingerprint on the star's outermost layers. Meanwhile, fresh hydrogen-rich material from the surface sinks inward, falls onto the neutron star, undergoes nuclear processing, and the cycle repeats. The entire star is a giant mixing machine, constantly cycling material between the neutron star at its heart and the surface where we can observe it. This means that the unusual elements produced by the IRP process on the neutron star's surface should eventually show up in the star's atmosphere. They should be detectable by spectroscopy, the technique astronomers use to analyze the light from a star and determine what elements are present in its outer layers. Every element absorbs and emits light at specific wavelengths. By examining the spectrum of a star, the pattern of absorption and emission lines in its light, astronomers can determine with remarkable precision what elements are present and in what quantities. A normal red supergiant has a well-known spectral signature. It contains specific amounts of specific elements, reflecting its mass, age, and evolutionary history. If a red supergiant showed anomalous abundances of certain elements that should not be there in those quantities according to standard stellar evolution models, that would be a powerful clue that something unusual is happening inside. And this is exactly what Thorne and Żytkow predicted. They and subsequent researchers worked out that a Thorne Żytkow object should show distinctive overabundances of several specific elements in its surface layers. The most important of these are lithium, rubidium, and molybdenum. These three elements, along with others like strontium and calcium, form the chemical signature that would distinguish a Thorne Żytkow object from an ordinary red supergiant. Let me tell you why each of these elements is significant. Lithium is one of the lightest elements. It is element number 3 on the periodic table. In most stars, lithium is actually destroyed rather than created. The temperatures inside stellar interiors are high enough to break lithium apart through nuclear reactions. As a star ages and its convective envelope mixes surface material down into hotter layers, lithium gets progressively depleted. Old stars, especially giant and supergiant stars that have deep convective envelopes, tend to have very little lithium left in their surface layers. Finding a red supergiant with an unusually high abundance of lithium would be suspicious. It would suggest that lithium is being created somewhere inside the star, faster than it is being destroyed, which is not something that happens in normal stellar interiors. In a Thorne Żytkow object, lithium can be produced through a specific reaction pathway involving beryllium. Material circulating near the neutron star is exposed to extreme conditions that can produce beryllium-7, a radioactive isotope. If this beryllium-7 is carried outward by convection quickly enough, before it can be destroyed by further nuclear reactions in the hot interior, it decays into lithium-7 in the cooler outer layers of the star. This is a known mechanism for lithium production, and it is particularly efficient in a Thorne Żytkow object because the convective circulation is vigorous and the temperature contrast between the neutron star's vicinity and the outer envelope is enormous. The beryllium gets manufactured in the intense heat near the center and transported to safety in the cool envelope before it can be destroyed, where it decays into lithium that accumulates on the surface. Rubidium is element 37, a heavier element that is relatively rare in most stars. In normal stellar nucleosynthesis, rubidium is produced in small quantities through a process called the slow neutron capture process, or ETSI process, which occurs in the interiors of asymptotic giant branch stars. The S process builds up heavy elements gradually by capturing neutrons one at a time, with beta decays occurring between captures. This is a slow, methodical process that produces a specific pattern of heavy element abundances. A Thorne Żytkow object, with its IRP process, produces rubidium through a completely different pathway. Instead of slow neutron capture, the rubidium is built up through rapid proton captures on the neutron star's surface. The material is then mixed outward into the envelope. The result is a rubidium abundance that is much higher than what you would expect from normal S-process nucleosynthesis. The overabundance is not just slightly elevated. Theoretical models predict it should be dramatically enhanced, potentially by factors of 10 or more compared to what a normal supergiant of similar mass and age would show. Molybdenum is element 42, another heavy element that serves as a diagnostic signature. Like rubidium, molybdenum is produced through the RP process in quantities that far exceed what normal nucleosynthesis would generate. Its presence in abnormally high concentrations on the surface of a red supergiant would be another piece of evidence pointing toward a Thorne Żytkow object. No known process in ordinary stellar evolution can produce the specific combination of enhanced lithium, rubidium, and molybdenum that the Thorne Żytkow models predict. Each element individually might be explainable through other mechanisms. A star might have high lithium for one reason, high rubidium for another, but finding all three simultaneously, in the right ratios, in a star that otherwise looks like a normal red supergiant, that would be extraordinarily difficult to explain without invoking a neutron star at the center. There are other elements in the predicted signature as well. Calcium and strontium can also be enhanced. The overall pattern of heavy element abundances is distinctive because the IRP process produces a specific distribution of isotopes that differs from both the S process and the rapid neutron capture process, called the R process, that occurs in supernova explosions and neutron star mergers. The chemical fingerprint of a Thorne Żytkow object is, in theory, unique. It should not be mimicked by any other known astrophysical process. At least, that is what the models predict. Whether nature cooperates with the models is another question entirely. Now, let me address something important. The fact that a Thorne Żytkow object would look almost exactly like a normal red supergiant from the outside is both its most fascinating feature and its most frustrating one. It is fascinating because it means the universe could contain these extraordinary hybrid objects, stars with neutron star hearts hiding in plain sight among the population of ordinary supergiants. Every time you look at a red supergiant through a telescope, you have to wonder whether it might be one of these. Is that just a dying massive star? Or is there something unimaginable buried at its center? But it is also frustrating because it makes detection incredibly difficult. Consider the challenge from an observer's perspective. You are looking at a red supergiant. It has the right color, the right brightness, the right size. Its surface temperature is somewhere around 3,000 to 4,000 degrees Celsius. Its luminosity is tens of thousands or hundreds of thousands of times that of the sun. It varies in brightness slightly over time, as many supergiants do. From every basic observational standpoint, it looks normal. The only way to tell if it harbors a neutron star at its center is to take a detailed spectrum and look for those subtle chemical anomalies. Enhanced lithium, enhanced rubidium, enhanced molybdenum. These are not obvious features. They require careful, high-resolution spectroscopy, the kind that can only be done with large telescopes and sensitive instruments. And even then, the interpretation is not straightforward. You have to measure the abundances precisely. You have to compare them to models of normal supergiant evolution to determine whether they are genuinely anomalous. You have to rule out other possible explanations for any anomalies you find. It is painstaking, detailed work with many opportunities for ambiguity and disagreement. There is another complication. Red supergiants are not simple, well-behaved objects. They are enormous, dynamic, and messy. Their surfaces are covered with convective cells, giant plumes of rising and sinking gas that create a mottled, irregular surface. Their spectra are complicated by molecular absorption bands because their surface temperatures are cool enough for molecules to form in their atmospheres. Titanium oxide, water vapor, carbon monoxide, and other molecules create dense forests of spectral lines that can overlap with and obscure the lines from the elements you are trying to measure. Analyzing the spectrum of a red supergiant is inherently more difficult than analyzing the spectrum of a hotter, simpler star. Add to this the fact that many red supergiants lose mass through powerful stellar winds, and the wind material can create circumstellar shells and disks that further complicate the spectral analysis. The environment around a red supergiant is dusty, dynamic, and difficult to model precisely. All of this means that detecting the subtle chemical signatures of a Thorne Żytkow object requires not just good data, but also sophisticated modelling and careful interpretation. There is yet another layer of difficulty. A Thorne Żytkow object is not expected to last forever. The neutron star at the centre is continuously accreting material. As it accretes, it grows more massive. If its mass exceeds a critical threshold, roughly 2 to 2.5 times the mass of the Sun, depending on the equation of state of neutron star matter, it will collapse into a black hole. Once that happens, the Thorne Żytkow object ceases to exist in its current form. The black hole may continue to accrete the envelope material, or the envelope may be disrupted. But the distinctive Thorne Żytkow configuration is gone. This means that even if these objects do form, they have a limited lifetime. Theoretical estimates for how long a Thorne Żytkow object can persist vary widely, from a few tens of thousands of years to perhaps a few 100,000 years. In astronomical terms, this is extremely brief. A normal red supergiant phase lasts a few 100,000 to 1,000,000 years. A Thorne Żytkow phase would be a fraction of that. This brevity makes them even harder to find. Even if they form regularly, there would be very few in existence at any given time because each one lasts only a short while before the neutron star either collapses into a black hole or the envelope is lost. Let me also address what a Thorne Żytkow object is not, because there are several related concepts that can cause confusion. A Thorne Żytkow object is not a neutron star binary. In a typical neutron star binary system, the neutron star orbits outside a companion star. It may accrete material from the companion through a stream of gas or an accretion disk, and this accretion produces X-rays that we can detect. But the neutron star is separate from the companion. It is in orbit around it, not inside it. A Thorne Żytkow object is something qualitatively different. The neutron star is embedded within the companion. It is surrounded on all sides by the companion's envelope. There is no accretion disk in the conventional sense. There are no X-ray emissions escaping the star, because any X-rays produced near the neutron star are absorbed by the enormous amount of overlying material before they can reach the surface. This last point is worth emphasizing. You cannot detect a Thorne Żytkow object by looking for X-rays. In a normal X-ray binary, the accretion onto the neutron star happens in a near vacuum, and the X-rays produced can escape into space and be detected by X-ray telescopes. In a Thorne Żytkow object, the accretion is happening deep inside a star, buried under hundreds of millions of miles of gas. Any high-energy radiation produced at the neutron star's surface is absorbed and thermalized by the envelope, long before it reaches the surface. By the time the energy emerges from the star, it's been converted from X-rays into ordinary optical and infrared radiation, indistinguishable from the normal thermal emission of a red supergiant. The neutron star is effectively invisible to direct detection. You cannot see it. You cannot detect its radiation. You cannot measure its spin or its magnetic field. The only evidence of its existence comes indirectly, through the chemical anomalies it produces in the star's surface composition. A Thorne Żytkow object is also not the same as a star that has simply undergone a merger with another normal star. When two normal stars merge, the result is typically a larger, more massive star with a mixed composition. But the core of the merged star is still a normal stellar core, made of dense gas undergoing nuclear fusion. The physics of the interior is still ordinary stellar physics, just with more mass and a more complicated history. A Thorne Żytkow object has a fundamentally different interior. Its core is not gas undergoing fusion. Its core is a solid, neutron-degenerate object, a neutron star, and the physics governing its behavior is neutron star physics, not ordinary stellar physics. The energy generation, the nucleosynthesis, the internal structure, all of it is different. And it is also not a star in the process of collapsing or exploding. A Thorne Żytkow object, if the theoretical models are correct, is in a state of quasi-equilibrium. It is not actively being destroyed. It is not in the middle of a catastrophe. It is functioning, in its own strange way, as a stable stellar object. It is generating energy through accretion. It is transporting that energy outward through convection. It is radiating from its surface. It is doing all the things a star does, just with a completely alien power source at its center. It is, in a sense, a new kind of star. Not a normal star, not a neutron star, not a binary system. Something else entirely. A hybrid object that combines elements of stellar physics and compact object physics in a way that nothing else in the universe does. This uniqueness is what makes the theoretical study of Thorne Żytkow objects so compelling. They exist at the intersection of two normally separate branches of astrophysics. Stellar evolution, which deals with how normal stars live and die, and compact object physics, which deals with neutron stars, black holes, and the extreme conditions around them. In most situations, these two branches do not overlap. Stars and compact objects interact from a distance, in binary systems. But in a Thorne Żytkow object, they are literally merged. The compact object is inside the star. The two branches of physics are forced to coexist in a single object. Studying these objects, even theoretically, requires combining knowledge from both fields in ways that are challenging and sometimes contradictory. The theoretical picture then is this. A Thorne Żytkow object is a red supergiant with a neutron star at its center. It looks almost normal from the outside. It is powered by accretion onto the neutron star, rather than by conventional nuclear fusion. Material from the envelope falls onto the neutron star, undergoes exotic nuclear reactions through the IRP process, producing unusual elements including lithium, rubidium, and molybdenum. These elements are mixed outward through the star's convective envelope and deposited on the surface, where they can be detected through high-resolution spectroscopy. The object has a limited lifetime, perhaps a few 100,000 years, before the neutron star accretes enough mass to collapse into a black hole. During its brief existence, it masquerades as an ordinary supergiant, hiding its extraordinary secret beneath a mundane exterior. This gives astronomers a recipe. If you want to find a Thorne Żytkow object, you look at red supergiants. You take their spectra. You measure their chemical abundances with as much precision as you can, and you look for stars that have too much lithium, too much rubidium, too much molybdenum, more than any model of normal stellar evolution can explain. If you find such a star, you have a candidate, not proof, a candidate. Because as we are about to see, the gap between a candidate and a confirmed detection is enormous, filled with uncertainty, alternative explanations, and the ever-present question of whether the models we are using to predict what a Thorne Żytkow object should look like are themselves correct. So the theory gives us a recipe. It tells us what to look for. A red supergiant with anomalous surface abundances of lithium, rubidium, and molybdenum, elements that should not be present in those quantities in any normal star at that evolutionary stage. The theory also tells us roughly where to look. Among the population of red supergiants in our galaxy and in nearby galaxies, any one of them could potentially be a Thorne Żytkow object in disguise. The question that has haunted astrophysicists for decades since Thorne and Żytkow published their original paper in 1975 is whether anyone has ever actually found one. And the answer to that question is complicated. It is not a clean yes, and it is not a clean no. It is something in between, something frustrating and fascinating in equal measure. The search for Thorne Żytkow objects began in earnest in the 1980s and 1990s. Astronomers started taking detailed spectra of red supergiants, looking for the predicted chemical anomalies. This was not easy work. As I described earlier, the spectra of red supergiants are complex, crowded with molecular absorption bands that make it difficult to measure individual element abundances with high precision. And the predicted anomalies are subtle. You're not looking for a star made of entirely different elements. You are looking for a star that has slightly too much of certain specific elements compared to what models predict. The signal is small, the noise is large, and the models themselves have uncertainties that make interpretation difficult. Early searches produced some intriguing candidates, but nothing definitive. Several red supergiants were identified with unusual chemical abundances, but in each case, alternative explanations could not be ruled out. Perhaps the star had undergone an unusual mass transfer event from a companion. Perhaps the models of normal stellar nucleosynthesis were incomplete. Perhaps there were measurement errors. The field remained in a state of tantalizing ambiguity for decades. There were hints, but no smoking gun. Then, in 2014, a team of astronomers led by Emily Levesque published a paper that changed the conversation. Levesque and colleagues had been studying a sample of red supergiants in the Small Magellanic Cloud, a small satellite galaxy of the Milky Way located about 200,000 light-years from Earth. The Small Magellanic Cloud is a useful laboratory for studying stars, because all the stars in it are at roughly the same distance from us, which eliminates one of the major uncertainties in stellar observations. When you observe stars in our own Milky Way, they are at wildly different distances, and distance uncertainties can affect your estimates of luminosity, mass, and other properties. In the Small Magellanic Cloud, this problem largely goes away. The team used the 6.5-meter Magellan Clade telescope at Las Campanas Observatory in Chile, one of the most powerful optical telescopes in the Southern Hemisphere. The location matters because the Small Magellanic Cloud is only visible from the Southern Hemisphere, hanging in the sky near the South Celestial Pole. From Chile's Atacama Desert, where the air is thin and dry and the skies are among the clearest on Earth, the telescope could gather enough light from individual stars in the Small Magellanic Cloud, 200,000 light-years away, to take detailed spectra. Each spectrum is a rainbow of light from a single star, spread out by a spectrograph into its component wavelengths, revealing the chemical fingerprint of the star's atmosphere. The team observed a sample of red supergiants in the cloud, carefully measuring the strengths of absorption lines corresponding to various elements, building up a picture of what each star was made of. Among the stars they studied, one stood out. It was designated HV2112. On the surface, it appeared to be a fairly ordinary red supergiant. It had the right colour, the right brightness, the right temperature. There was nothing visually remarkable about it. It would not catch your eye in a photograph. It was just another red star among many in a small satellite galaxy. But when the team analysed its spectrum in detail, measuring the abundances of various elements in its atmosphere, they found something striking. HV 2112 had unusually high abundances of lithium, rubidium, and molybdenum, all three of the key elements predicted by Thorne Żytkow theory. The overabundances were substantial. They were not marginal detections that could easily be dismissed as measurement noise. They were clear, well-measured enhancements that stood out compared to other red supergiants in the same sample. Consider what it must have been like for the team when the results came in. You are analysing spectra of several red supergiants, one by one, measuring element abundances, comparing them to models. Most of the stars look normal. Their chemical compositions match what you would expect. And then you get to HV 2112, and the lithium line is too strong. The rubidium line is too strong. The molybdenum line is too strong. All three, all at once, in a single star. You check your work. You re-examine the spectrum. You look for systematic errors, problems with the data reduction, contamination from other sources. And the anomalies hold up. They are real. The star has too much of exactly the elements that Thorne Żytkow theory predicts. After decades of searching by many astronomers, you may be looking at the first real candidate. The announcement generated significant excitement in the astrophysics community. Here, for the first time, was a star that matched the predicted chemical signature of a Thorne Żytkow object. Not just one anomalous element, but the full set of three key elements, all enhanced simultaneously in a star that otherwise looked like a normal red supergiant. Levesque and colleagues were careful in their language. They didn't claim to have definitively discovered a Thorne Żytkow object. They described HV 2112 as the strongest candidate to date, noting that the chemical abundances were consistent with Thorne Żytkow predictions, but also acknowledging that further study was needed. And further study revealed complications. Because here is the thing about astronomy, about science in general. Finding a candidate is not the same as proving the case, and proving the case for a Thorne Żytkow object is extraordinarily difficult because you cannot directly observe the neutron star at the center. You cannot take a picture of it. You cannot detect its X-rays because they are absorbed by the envelope. You cannot measure its gravitational field directly because it is hidden inside a much larger star. All you have are the surface chemical abundances, and those abundances, while consistent with Thorne Żytkow models, might also be consistent with other explanations. The most significant alternative explanation involves a class of stars called super-asymptotic giant branch stars, often abbreviated as Super AGB stars. These are massive stars in a late stage of evolution where they have developed very deep convective envelopes and are undergoing complex nucleosynthesis in their interiors. Super AGB stars can produce unusual surface abundances through a process called hot bottom burning, where material at the base of the convective envelope is exposed to temperatures high enough to trigger nuclear reactions. These reactions can produce some of the same elements that Thorne Żytkow models predict, including enhanced lithium and certain heavy elements. Let me explain why the Super AGB alternative is so troublesome. A Super AGB star is a star in a mass range of roughly 8 to 10 times the mass of the Sun that is in one of the final stages of its evolution. It has exhausted its core hydrogen and helium, and is burning fuel in shells around a dense core made of oxygen, neon, and magnesium. Its envelope is enormous, fully convective, and actively mixing material between the surface and the deep interior. At the base of the convective envelope, temperatures reach high enough for nuclear reactions to occur, reactions that can produce lithium through the beryllium transport mechanism I described earlier, and that can also produce certain heavy elements through neutron capture processes. The surface of a super AGB star can show enhanced lithium and enhanced abundances of some heavy elements, not for the same reasons as a Thorne Żytkow object, but through different physical mechanisms that produce superficially similar results. The question then becomes whether you can distinguish between a Thorne Żytkow object and a super AGB star based on surface abundances alone. And the honest answer is that it is very difficult. The predicted abundance patterns are different in detail. A Thorne Żytkow object should produce a specific ratio of rubidium to other heavy elements that differs from what hot bottom burning produces. The molybdenum enhancement is thought to be more distinctive because it is harder to produce through normal AGB nucleosynthesis. But in practice, the differences are subtle enough that measurement uncertainties and modeling uncertainties can blur the distinction. A star that looks like a Thorne Żytkow candidate could potentially be an unusual super AGB star. And the reverse is also true. There was also a more fundamental question raised about HV 2112. Some researchers challenged the basic classification of the star, arguing that it might not be a red supergiant at all. This matters enormously because supergiants and super AGB stars occupy different regions of the brightness scale. A true red supergiant is more luminous than a super AGB star. If HV 2112 were actually a super AGB star, its luminosity would be lower than that of a true supergiant, and the chemical anomalies could be explained without invoking a neutron star at the center. The distinction hinges on the star's luminosity, and measuring the luminosity of a star 200,000 light-years away requires knowing the distance precisely, accounting for the dimming effects of interstellar dust, and correctly interpreting the star's spectrum to determine its temperature and radius. Subsequent observations attempted to pin down the star's luminosity more precisely to settle this question, but the results were ambiguous. Different studies using different methods arrived at different conclusions. Some supported a high luminosity consistent with a supergiant classification. Others suggested a lower luminosity more consistent with an AGB star. The problem is that the boundary between supergiants and the brightest AGB stars is not a sharp line. It is a blurry zone where the two populations overlap in temperature and brightness, and placing a single star on one side or the other with confidence requires extremely precise measurements. This kind of back and forth is common in frontier science. When you are trying to identify something that has never been confirmed before, where the observational signatures are subtle and the theoretical predictions have uncertainties, disagreements are inevitable. No single observation can settle the question. What is needed is convergent evidence from multiple independent lines of investigation. You need the chemical abundances to match. You need the luminosity to be consistent. You need to rule out all plausible alternative explanations. And ideally, you need additional independent evidence. Something beyond just surface chemistry that points to a neutron star at the center. What would such additional evidence look like? Several possibilities have been discussed. One is neutrino emission. A neutron star accreting material inside a supergiant would produce neutrinos through nuclear reactions on its surface. These neutrinos, unlike photons, could potentially escape the stellar envelope because neutrinos interact very weakly with matter. A burst of neutrinos from the direction of a Thorne Żytkow candidate, correlated with some observable change in the star, could provide strong evidence. But current neutrino detectors are not sensitive enough to detect the low flux expected from a Thorne Żytkow object at the distance of the Small Magellanic Cloud. We can detect neutrinos from a supernova in a nearby galaxy, but the steady, low-level neutrino emission from accretion onto a neutron star buried in a supergiant would be far too faint. Another possibility is gravitational waves. If the neutron star at the center is spinning rapidly and has an asymmetry, it could produce continuous gravitational waves. Current detectors like LIGO and Virgo are not sensitive enough to detect such waves from a Thorne Żytkow object at interstellar distances, but future detectors might be. This remains a purely theoretical possibility for now. A third possibility is the eventual fate of the object. If a Thorne Żytkow object exists, the neutron star at its center will eventually accrete enough mass to collapse into a black hole. This collapse might produce a detectable event, perhaps a burst of neutrinos, perhaps a change in the star's behavior, perhaps an unusual supernova. If astronomers could catch a Thorne Żytkow object in the act of transitioning, watching the neutron star collapse and the star respond, that would be powerful evidence. But since this transition is expected to be rare and brief, the chances of observing it are extremely small. There have been other Thorne Żytkow candidates proposed over the years, though none have received as much attention as HV 2112. Aquarii, a star in our own galaxy, was considered at one point because of its unusual chemical composition, particularly its carbon and S-process element abundances. However, subsequent analysis suggested it was more likely a born-again asymptotic giant branch star, a star that experienced a late thermal pulse after initially evolving off the AGB rather than a Thorne Żytkow object. VZ Sagittarii was another star that attracted some interest, but again, the evidence was not strong enough to make a compelling case. The rarity of strong candidates is itself informative. If Thorne Żytkow objects were common, we would expect to have found several clear examples by now. The fact that after decades of searching, we have only one strong candidate and a handful of weaker ones suggests one of several possibilities. Either Thorne Żytkow objects are extremely rare, forming so infrequently that there are very few in any given galaxy at any given time, or they are so short-lived that even if they form at a reasonable rate, only a tiny number exist at any moment, or the formation channel is even narrower than theoretical models suggest, requiring such specific conditions that nature rarely produces them, or perhaps they do not form at all, and the theoretical prediction, while mathematically consistent, does not correspond to anything that actually happens in the real universe. Any of these possibilities is consistent with the current data. We simply do not know which one is correct. Let me talk about the broader significance of this uncertainty. Science is full of theoretical predictions that took decades or even centuries to confirm or refute. Gravitational waves were predicted by Einstein in 1916, but not detected until 2015, nearly a century later. The Higgs boson was predicted in 1964 and confirmed in 2012, almost 50 years later. Black holes were predicted as mathematical solutions to Einstein's equations long before we had any observational evidence for their existence. The history of physics is a history of theoretical ideas waiting for technology and opportunity to catch up. Thorne Żytkow objects may be in the same category. The idea was proposed in 1975. We are now 50 years into the search. We have one strong candidate and ongoing debate about its true nature. This is not unusual for a theoretical prediction involving rare, short-lived, and observationally subtle objects. The fact that we have not confirmed one yet does not mean they do not exist. It means we have not yet gathered sufficient evidence to be sure. Future observations may change the picture. The next generation of large telescopes, including ground-based observatories with primary mirrors 30 meters across or larger, will be able to take higher resolution spectra of red supergiants in nearby galaxies with far greater precision than current instruments allow. 3 major projects are under development. The Extremely Large Telescope, or ELT, being built by the European Southern Observatory in Chile's Atacama Desert, will have a primary mirror 39 meters across. The 30-meter telescope, or TMT, planned for Mauna Kea in Hawaii, will have a mirror 30 meters across. And the Giant Magellan Telescope, or GMT, also being built in Chile, will combine 7 mirrors to create an effective aperture of 25 meters. These instruments represent a quantum leap in capability. They will collect far more light than current telescopes, which means they can take detailed spectra of fainter and more distant stars. They will have better spectral resolution, which means they can distinguish between closely spaced absorption lines more cleanly, measuring individual element abundances with far greater precision, and they will have adaptive optic systems that correct for the blurring effects of Earth's atmosphere, producing sharper images and cleaner data. What this means for the search for Thorne Żytkow objects is significant. With current telescopes, we can take detailed spectra of the brightest red supergiants in the Small Magellanic Cloud, 200,000 light-years away. But the data are noisy and the measurements have substantial uncertainties. With a 39-meter mirror, we could do the same observations with far better precision. We could measure lithium, rubidium, and molybdenum abundances to much tighter tolerances. We could look for subtler differences in the abundance patterns that would help distinguish between Thorne Żytkow objects and super AGB stars. We could also extend the search to more distant galaxies, surveying larger populations of red supergiants to find additional candidates. More precise luminosity measurements from space-based observatories will help settle the question of whether candidates like HV 2112 are true supergiants or AGB stars. Improved theoretical models of both Thorne Żytkow objects and super AGB stars will sharpen the predicted differences between the two, making it easier to distinguish them observationally. Time domain astronomy, the systematic monitoring of stars for changes in brightness and behavior, might catch a Thorne Żytkow object in the act of transitioning, revealing itself through some observable change. There is also the possibility that the chemical signature approach, while valuable, is not the best way to find these objects. Perhaps future researchers will develop entirely new detection methods that we have not yet conceived. The history of astronomy is full of objects that were discovered through methods nobody anticipated. Pulsars were discovered by accident by Jocelyn Bell Burnell in 1967, while she was studying something else entirely. Gamma-ray bursts were discovered by military satellites designed to detect nuclear weapons tests, not astronomical phenomena. Science has a way of finding things through unexpected channels. It is entirely possible that the first confirmed Thorne Żytkow object will be identified through some method that nobody has thought of yet. Let me step back now and consider what the existence or non-existence of Thorne Żytkow objects tells us about the universe. Because regardless of whether these objects turn out to be real, the question itself is profound. It asks us to consider the limits of what is physically possible. Can two objects as radically different as a neutron star and a red supergiant coexist in a single structure? Can the most extreme form of matter in the universe be hidden inside the most diffuse? Can the universe produce objects that seem to violate our basic intuitions about how things should work? The fact that we cannot immediately answer no to any of these questions tells us something important about the universe's creativity. Nature is not limited by our intuitions. It is not constrained by what seems reasonable or sensible to a species that evolved on one small planet to deal with objects at human scales. The universe operates according to physical laws, and those laws permit a far wider range of possibilities than our imaginations would suggest. Thorne Żytkow objects, whether they exist or not, represent one of those possibilities. They sit at the boundary of what we think is possible, challenging us to refine our understanding and to keep looking. And there is a philosophical dimension to this story as well. The idea that something as extreme as a neutron star could be hiding inside something as apparently ordinary as a red supergiant is a powerful metaphor for how appearances can deceive. In astronomy, as in life, the surface does not always reveal what lies beneath. A star that looks normal might harbor an extraordinary secret. An object that appears mundane might be one of the rarest and most unusual things in the universe. The only way to know is to look more closely, to measure more precisely, to ask better questions, and to be willing to accept answers that challenge our assumptions. The current scientific status of Thorne Żytkow objects can be stated clearly. They are a well-established theoretical prediction, first proposed in 1975 by Kip Thorne and Anna Żytkow. The physics underlying the prediction is sound, based on well-understood principles of stellar evolution, binary star interactions, common envelope evolution, and nuclear physics. The theory makes specific, testable predictions about what these objects should look like, particularly regarding unusual chemical abundances on the surface. One strong candidate, HV 2112, in the Small Magellanic Cloud, has been identified with chemical abundances consistent with the predictions. However, the candidate remains unconfirmed. Alternative explanations, particularly super AGB star nucleosynthesis, cannot be ruled out with current data. No Thorne Żytkow object has been definitively confirmed to exist. The concept remains one of the most tantalizing unverified ideas in stellar astrophysics, sitting in the gap between theoretical prediction and observational confirmation. That gap is where some of the most exciting science happens. It is the space where theory and observation meet, challenge each other, and drive each other forward. Every unconfirmed prediction is an invitation, a challenge to build better instruments, take better data, develop better models, and look more carefully at the universe. Thorne Żytkow objects are one such invitation, and the astrophysics community has been responding to it for 5 decades. The search continues, and in a way, that is the most remarkable part of this entire story. Not the neutron star at the center, not the exotic nucleosynthesis, not the candidate in a distant galaxy. The most remarkable part is that 2 physicists sitting at their desks in 1975, working through equations on paper, predicted that the universe might contain an object so strange that it would take half a century and counting for observers to determine whether it actually exists. They imagined something that had never been seen, something that challenged basic assumptions about stellar structure, something that sounded impossible. And then they showed, through careful mathematical reasoning, that it might not be impossible after all, that the laws of physics, if arranged just right, might permit this extraordinary configuration, that nature, given enough opportunities, might actually produce it. That is what theoretical physics does at its best. It reaches beyond what we have observed and asks what else might be out there. It uses the laws we have discovered to predict things we have not yet found. Sometimes those predictions are confirmed quickly. Sometimes they take decades. Sometimes they are never confirmed because nature does not cooperate. But each prediction pushes our understanding forward, whether it turns out to be right or wrong. And in the case of Thorne Żytkow objects, the prediction has inspired 50 years of observational work, theoretical refinement, and cross-disciplinary collaboration between stellar astronomers and compact object physicists. It has deepened our understanding of common envelope evolution, of exotic nucleosynthesis, of the limits of stellar structure. Even if we never confirm a single Thorne Żytkow object, the idea itself has been scientifically valuable because of the questions it forced us to ask and the knowledge we gained by trying to answer them. But I suspect we will find one eventually. The universe has a way of being stranger than we expect. Every time we have predicted something based on solid physics and then looked hard enough with good enough instruments, we have usually found it. Gravitational waves, black holes, exoplanets, neutron stars themselves were once a purely theoretical prediction. In 1934, Walter Baade and Fritz Zwicky proposed that neutron stars might form in supernova explosions. It took over 3 decades until Jocelyn Bell Burnell discovered pulsars in 1967, before we had observational proof that they existed. 33 years from prediction to confirmation. Thorne Żytkow objects have been waiting 50 years. They may have to wait longer still, but the universe is patient. And so are the astronomers searching for them. So the next time you look up at the night sky and see a bright red star, perhaps Betelgeuse in the constellation Orion, take a moment to wonder. That star is a red supergiant. It looks like an ordinary dying star, and it almost certainly is an ordinary dying star. But consider the possibility, however remote, that something stranger might be happening inside. Consider the possibility that somewhere out there, perhaps in our galaxy, perhaps in a neighboring one, there is a red supergiant that harbors a neutron star at its heart. A star that looks normal on the surface but is unlike anything else in the universe. A Thorne Żytkow object, hiding in plain sight, waiting to be found. The universe is full of things we have not yet discovered. Some of them are subtle, hidden behind the familiar appearance of objects we think we understand. The cosmos does not always advertise its strangeness. Sometimes it hides the extraordinary inside the ordinary, the impossible inside the mundane, the astonishing inside the apparently simple. And the only way to find those hidden wonders is to keep looking, keep measuring, keep asking questions, and keep being willing to be surprised by the answers. That is what makes science extraordinary. Not that it gives us certainty, it often does not, but that it gives us the tools to peel back the surface of the universe and glimpse what lies beneath. One layer at a time, one measurement at a time, one strange prediction at a time. Thank you for spending this time with me exploring one of the most unusual ideas in all of astrophysics. If this kind of deep exploration fascinates you, a like or a subscribe would mean the world to me. It helps the channel grow and keeps these journeys going. The universe is full of hidden wonders, and we have only just begun to find them. Good night. And the next time you look up at the stars, remember that some of them might not be what they seem.